Have you ever noticed the many different types of wings that aircraft have? There's traditional planes like the Boeing 737, which I'll actually be riding home in a couple of days, which has your traditional airplane wing. There's simple triangular, or more like trapezoidal bars that stick out of the body of the plane. But then there's things like the Northrop B-2 Spirit bomber that just completely break the norm. This plane looks so sleek, it doesn't look like it should be able to fly. It just goes against your typical plane with its jagged edges and all-in-one design, with the wings being part of the fuselage. But why is this possible? How can wings be so different? Well, all of that comes down to airfoils. If you were to cut apart an airplane wing widthwise, you would be able to see its airfoil. An airfoil is a shape designed to manipulate fluid in order to achieve a certain reaction. That's kind of a general definition, but in planes they're typically designed to reduce drag and maximize lift so that the plane can fly. So now we're getting into airfoil anatomy. So once again, we've cut a wing and are looking at its cross section. For right now, we'll say this is what a typical airfoil looks like. And here I'll just kind of go and explain what each part is, and don't worry about the diagram because it's a lot simpler than it looks. Alright, so I'll begin with the simple stuff. The leading edge of an airfoil is basically exactly what it sounds like. It's just the frontmost part of the airfoil, or the part that first meets air, if you want to get a bit more technical. Following this train of thought is the trailing edge, which is the rearmost part of the airfoil. The chord is an imaginary line connecting the leading and trailing edges. The upper edge is the upper surface of the airfoil, and the lower edge is the lower surface. Camber is a measure of the curvature of the airfoil. It's also represented by a line connected by the leading and trailing edges. And we have one more term. The angle of attack is the angle made between the chord line of the airfoil and oncoming airflow. Alright, so I lied. There's some other terms when it comes to the basics of flight. But the good thing is you're probably most likely already familiar with them. There's weight, and this is the force dragging something down. It's counteracting force lift, which pushes an object up. There's thrust, which I like to think as the force that pushes an object forward. And its counteracting force is drag, which opposes this forward motion. Things fly when lift is greater than weight, and things move forward when thrust is greater than drag. I mentioned this before, but the general point of an airfoil is to maximize lift and reduce drag to make something fly. Altering these different characteristics changes the performance of an airfoil and ultimately the performance of the wing. Planes ultimately fly up by pushing air down using their wings. This follows Newton's third law of motion, where air reaction has an equal and opposite reaction. The other planes, like the Wright Flyer, had poor lift efficiency on their wings, and they had to compensate with this by using higher angles of attack to push more air down and, make the plane fly. When air hits the leading edge of an airfoil, airflow is split and travels into the upper and lower edges of the airfoil. The curved top of the upper edge causes air to travel faster over it, creating an area of lower pressure. The lower edge has less curvature, so air will travel slower, creating an area of lower pressure. These pressure differences maximize lift, allowing the plane to fly more efficiently. Nowadays, we have airfoils, and airfoils have been altered and designed to serve different purposes. Some maximize lift, some speed, and some maneuverability by changing aspects such as thickness, camber, and chord length. In fact, there are so many airfoils that the National Advisory Committee for Aeronautics, otherwise known as NACA, has developed a numbering system using a series of digits where each number represents a property about the airfoil. As an example, I use the NACA 4 series, which is like a set of airfoils basically. In the 4 series system, the first digit tells the camber, the second digit tells the location of the max camber, and again, remember that camber just means curvature. And the last two numbers represent the thickness of the airfoil. Alright, so as an example, we have the NACA 2412. So here, the camber is 2%. The location of max camber is 40% into the chord, which is told to us by before. And then lastly, the last two digits tells us that the thickness of the airfoil is 12%. Although the Central focused heavily on the aeronautics side of airfoils, It should be known that airfoils are not only found in the aviation industry, as my partner will hopefully tell you in the next video.